Just some miscellaneous stuff with proton NMR. When you put the sample into the NMR machine, it needs to be dissolved in some kind of solvent. Now you can use a special kind of water instead of normal hydrogen. You can use deuterium, which is an isotope of hydrogen, or you can use something called tetrachloromethane, CCl4. These are inert, they don't react with the sample and contain no hydrogen atoms, or the normal kind of hydrogen atoms, protons, so don't produce any peaks on the spectra. Moving on to rate equations. For rate equations, say for example if you had a rate where you had a rate constant multiplied by a to the power 2 and b to the power 1, the rate with respect to a is 2, rate with respect to b is 1, and the overall rate is 2 plus 1, which is 3. For the rate determining step, in a reaction which has a number of steps, you have to wait for 2 particles of A, because that's the rate with respect to A is 2. You have to wait for 2 particles of A and 1 of B to appear. So 2 particles of A because the rate with respect to A is 2, and 1 of B to appear because the rate with respect to B is 1. And so if we had, say for example, these steps here, A plus B goes to AB. Well, 1 particle of A has appeared and 1 particle of B, but I've got to wait for 2 particles of A to appear and 1 of B. So it's not in that step yet because I've not had 2 particles of A. Next step, AB, and A is used, so 2 particles of A and 1 of B have only appeared by the second step, so the rate determining step is step 2. The rate equation shows how the rate of a reaction changes if you change concentrations. But however, the rate of a reaction changes with things like temperature and adding a catalyst too. So these things, a temperature, a small increase in temperature leads to a huge increase in rate because many more particles have the required activation energy. So you raise the temperature by a small amount, that increases the number of particles, you get many more with the activation energy. And therefore the rate constant and the rate of reaction goes up. Much more so than, say for example, change in the concentration. Adding a catalyst, well, adding a catalyst also speeds up a reaction. The way that that does that is that the way that the particles comes together changes when you add a catalyst. That's called the root of the reaction. And the activation energy is lowered by a catalyst, so more particles have that minimum energy needed to react. The catalyst doesn't appear in the rate equation, so in here, say for example A or B are not catalysts, the catalyst doesn't appear in that rate equation. Okay. Finally, there's something called the Arrhenius equation. You'll be given this equation that looks like that. ln is a form of logarithm. It's not the normal log that you've seen in, say for example, pH equals minus log to the base 10. It's not that kind of log, it's ln. And ln will appear on a calculator. It's something called a natural log, and there's an ln button on your calculator. K is the rate constant. A is another number called the Arrhenius constant, which you'll be given. ln is a button on your calculator, EA is the activation energy, R is the gas constant, 8.31, and T is the temperature in Kelvin. And so what you'll be asked to do with this is a little bit of maths. So there's 2 things it can ask you. One is to do a little bit of maths. Let's have a look at a little bit of maths. In a minute we'll just have a few other questions as well. So say for example the rate equation here is rate is K to the power E. First question, explain why doubling the temperature has a much greater effect on the rate of the reaction than doubling the concentration of A. We've said previously that a reaction occurs when molecules have the activation energy, and doubling the temperature gives many more particles this energy, whereas doubling the concentration doesn't have the same effect, it only doubles the number of collisions. Increased concentration means there's more collisions. Here we have an Arrhenius equation 1, so to go back to this one, natural log ln on your calculator of the rate constant equals ln button on your calculator of the Arrhenius number, activation energy, gas constant, temperature in Kelvin. You'll be given all that, and you'll be given some numbers to plug in. So let's have a look at this. We've been given some numbers. We've been given K, we've been given the rate equation, the Arrhenius equation, ln of K equals ln of A, the Arrhenius number, take away activation energy, divided by gas constant, divided by temperature in Kelvin. And so we're given all these numbers. A is 2.57 times 10 to the power of 10, gas constant 8.31. And all you do is plug those numbers in. So let's have a look. Here's my Arrhenius equation that I've been given in the question. Log of K equals log of A, natural log, that is this button ln, take away activation energy divided by RT, gas constant, and temperature in Kelvin. You've been given K, you've been given the Arrhenius number, you've not got EA, that's what it wants you to find out in the question. Use this to calculate the activation energy. You've been given the gas constant and you've been given the temperature. Let's have a look how we rearrange this then. So I've just done 6.51 times 10 to the minus 3, pressed the natural log button on my calculator, ln, and it's come out as that number, minus 5.034. I've done the same for this number, 2.57 times 10 to the power of 10, press the log button and it's come out as this number, take away activation energy divided by these numbers, that comes out as 2493. I took this and hopped it over to the other side, the equal sign, and it becomes minus 23.97, so that takes us to this, minus 5.034, take away, because that's come across the other side, minus 23.97, equals now minus activation energy divided by this number, which was 8.31 times 300, and so we're very close now. We're here. These two numbers take away from each other, minus 29.004 equals minus activation energy divided by 2493. Don't like the two minus numbers, so I'm going to make them both positive. Whatever I do to one side is okay, as long as I do it to the other side on the equation. So 29.004 equals the activation energy divided by 2493. Take this across the other side of the equal sign. It's on the bottom on this side, on the top on the other side, and so 29.004 equals 2493, which is the activation energy. Okay, that's in joules. 72,306. I know it's in joules because the gas constant there is in joules, but it's actually asked me for it in kilojoules. So joules into kilojoules, I'm going to divide this number by 1,000. 72,306 equals 72.3. I've taken it to three significant figures because I've looked in the question, and I try not to have anything more than the number of significant figures in some of these. So 8.31, 1, 2, 3 numbers is three significant figures, so this one's to three significant figures too. Finally, what you can be asked to do is you can be asked to do this, and it leads you through the question. It's not tricky. It tells you what to do really with this Arrhenius equation. It gives you the Arrhenius equation. They've just moved those around slightly, but it's the same thing. And they've said to you, you've got a rate constant. Can you work out ln of k, the natural log of k? So all you do is you put 6.13 times 10 to the minus 5 into your calculator, press the natural log button, and give me an answer. Do the same for that, 2.75 times 10 to the minus 4, press the log button, it'll give you an answer. Same for that one, same for that one. Temperature, it wants 1 divided by temperature, so you put 1 divided by 700, it'll give you an answer. 1 divided by 727, give you an answer. 1 divided by this temperature, 1 divided by 745, give you an answer, and 1 divided by 793 will give you an answer. Okay, and it comes out as that. That's what it comes out as. Okay, that's just buttons onto a calculator. Next it says plot a graph of ln k, natural log k, against 1 divided by temperature. So when you do that, if it says plot a graph of ln k against 1 divided by temperature, this one goes up the y-axis and 1 divided by temperature goes along the bottom axis. That's what it means. Plot a graph of this against this. That goes up the side, this goes along the bottom, and use your graph to calculate a value of the activation energy. When you're asked to plot this graph, or if you're asked to plot this graph, I'll show you how to get the activation energy. It's the gradient of the line. So what you do is this: you get all of your numbers and you plot natural log of k up the side, 1 divided by temperature across the bottom or top, and you end up with a graph a little bit like that. Okay, if you notice, I have got my natural log of k down the side. I've started that as 0 because it seemed to fit, but across the top, these very small numbers, I've not taken it back to 0. So I think you'll find that 1 divided by temperature along the x-axis that's going across, you may find that it doesn't go back to 0. So don't worry about that. Don't get it back to 0. Your x-axis, 1 divided by temperature, just start at somewhere near your lowest number. Go up. I've gone up 1, 1, 11, I suppose, 12, 13, 14, 15, or 0.0011, 0.0012, 0.11, 0.0013, and so forth. And then I've gone down from that corner because these numbers are negative numbers here, and I've gone down, and then I've plotted them. So I've taken 1 divided by t was 0.00143, 0.00143, and I've come down here and put one at minus 9.6, 9.7, sorry, 0.00138, 0.00138 comes down to about minus 8.2. Yep, and I've plotted them, and then I've drawn a line through them. It should be a line of best fit. So your marks so far are for setting out the graph, putting ln log of k as a label down the side, 1 mark for labelling the axis, and 1 divided by temperature along the x-axis. So that's an easy mark. Putting the points on is another one. Putting a line of best fit through them all, and then finally what you do is, when you've got that line of best fit, you make a triangle out of it. That bottom red line's not quite straight on my computer, but you make a line down there and a line down there, and you take the measurement of the y that's going up and down, and so it starts at minus what have I done here? Here we go. Minus 0.06, minus 0.06 is where it starts, and it comes down to 10. I've made my triangle quite convenient in that way, and so I've worked out that it's gone down nearly minus 10. It's gone down by minus 9.94. So I've taken the two numbers away here, 0.06, and taken away 10, and I've realised it's coming down. So I'm going from here down to here, and so that's a negative value, minus 9.94. And then I'm going across, and I've worked out it's gone from minus 0.0011 up to about minus 0.00145, taking the 2 away, and it comes out as 0.00035. And that's a positive value because it's going up. So this one's coming down as we're going from this point to this point. This one's coming down on the y-axis, going across on the x-axis. So this is a minus number, this is a plus number. Your activation energy then will be change in y, in other words that's how far down it's come, divided by change in x, how far across it's come, minus 9.94 divided by 0.00035. It'll give you quite a big value, and it'll be minus because my slope's coming down. So it's a negative value, and that's your activation energy. Don't worry about units. You don't need to put units in because it will tell you that it's in the units in the is kilojoules per mole in the